Welcome everyone to this lecture. Today we'll be doing some questions, specifically on the topic of fluid mechanics. Uh, as I have found that the best way actually to understand any topic is usually by doing some questions in it. Theory, I can assume that you can get from any source. But basically, what insight we capture when we do some questions is something unparalleled, especially when we approach a question from a fresh point of view. Because a lot of times we are doing the same question again and again, so it does not give us any new things to learn about. So let's begin. Mainly, the idea of this whole video is to understand Bernoulli's theorem. So Bernoulli's theorem is basically in statement form is that half rho v square, uh, that is the kinetic energy term of the fluid flow, plus rho g h, that is the potential energy term of the fluid flow, plus pressure is a constant throughout the streamline of the flow of a fluid. So this means that if I have some kind of a tube, in that tube, at any point, if I were to take these three terms, that is the velocity of the fluid, the height of the fluid, or the height of the center of its cross section above some given datum level or some given reference, and the pressure in the fluid at that particular point. So there some remains a constant. So this is a consequence of conservation of energy. We say the energy of the fluid is conserved at all points in the streamline flow. So this is because in a streamline flow, the energy is not dissipated in other forms. There is no friction involved, no viscous forces are involved. Whereas in real life cases, there is always some viscosity. But we can approximate a bit of whatever physical quantities which we want to obtain using this equation. So they gave us a good perspective or a good estimate, what we can say. As we are learning about fluid flow, at this point of time, we must basically understand what is the ideal case. So that is the whole point. A lot of cases vary from each other in a lot of ways. But what is the one idea which governs them all? That is what we want to learn. So that is Bernoulli's equation. So besides Bernoulli's equation, when we derive Bernoulli equation, we also come about different equations called like velocity of efflux. The velocity of efflux is this equation v is equal to root 2 gy. So this equation tells us that if you have a container and you have poked a hole in this container at a depth of y, then the fluid will pour out uh, of this fluid at velocity v uh, at such a rate that it would depend upon the height at which the orifice is made uh, or we have poked the container. So at that particular y, v would be proportional to square root of that y distance. So this is called Torricelli's equation or Torricelli's law because it is named after him. But the interesting part is that this is just like the velocity of a particle if it has fallen through y height. That is when I release a particle, and let's say this pen only, I release it from y height. So it will gain v velocity. So that v velocity is this. But this is the case of fluid. How is that following this equation? So there's an easy way of remembering. Okay, just when a fluid particle falls through y height, so its velocity is root 2 gy. Very easy, right? So although things are not easy to learn when you're learning from the first way, but to learn that where this equation comes from, for that we can refer to Bernoulli's theorem. For that, we need to know what Bernoulli's theorem is. That the pressure per unit volume, kinetic energy per unit volume plus pressure in a fluid in a streamline remains constant throughout a steady and non-viscous flow of a fluid. So let's begin with our questions. So the question which we have is that of a tube. So this is the tube. This tube is placed inside a very interesting body of water. Interesting as in that the body is not stationary. That's what I mean. So basically, the speed of flow of a river. This is a river. So this river is basically flowing. So if you don't find rivers interesting, it's up to you. But it's basically flowing or something like that. And let's say it is flowing with a velocity of the v speed, and so it is flowing with this with a velocity v with respect to this tube. Okay, so you can assume that this tube is stationary in this river, and the river is flowing with the speed v. That speed v is given to us as 2.5 meter per second. So it is also given that the tube rises above this particular uh, surface of the river by a height h naught equal to some 12 centimeter. Right. So we have to find the maximum height to which water can spurt above the orifice. So I'll repeat the question again. Find the maximum height to which water can spurt above the orifice. So basically, the water will start coming out of this small orifice made in this tube, which is closed here, and made a small hole is made here. So water will start coming out like a fountain. Okay. Basically, this is like a how you can make a small fountain in a river. You can just put a tube and just attach it like that. So the kinetic energy of the river will be converted into potential energy of the water. So it will rise. Question is, till what height the water will rise? H. Okay. So it is a direct conversion of kinetic energy of the water into the potential energy of the water. Okay. So we will say half rho v square. That is the kinetic energy per unit volume of this fluid that is going inside will be equal to rho g, this height h naught. The water will rise up till this height h naught, and further when it goes out, comes out of the tube, it will rise this further height h. That is what we will say. And we'll ignore this part of the tube basically. We'll say this part of the tube, since the height is not given, we'll say it is negligible. And just as water is coming, the water will start losing its kinetic energy somewhere here. So it will gain this height h naught, and further it will rise with the height h. So what is happening is that at this point the fluid has some speed v dash. Okay, so when the fluid is coming out of this point v dash, it will start going in different directions. The one particle which is supposed to reach the highest point will lose all its velocity at the highest point, its speed would be 0. So at the highest point, that is height h, my half rho vy square, half rho v square term would be simply 0. And my height would be rho g h naught, that is the height I have given till this point, plus the height I have to gain this much. So this would be simply v is equal to 2g h naught plus h, or v square is equal to this. So 2.5 square is equal to 6.25 equal to 2 into 10. H naught plus h, that is 12 plus h. So we have to multiply this by 10 ki power uh, 2, because these distances 12 and h are in centimeter. So or minus 2, right? This is 12 centimeter, h is also in centimeter. So this is 10 ki power minus 2. So this would be 6.25 into 2.2 into 12 plus h. So this 6.25 by 2 means some 31.25 equal to 12 plus h. This implies this is some 21.25 minus 2. This is 19.25 centimeter height. So this is the height up till which the water will rise um, in this particular tube. The maximum height to which the water can spurt above the orifice, that would be 19.25. Next, we have a question of a tap, right? So we'll be using a lot of taps, right? And every day we basically use taps to wash our hands and to take bath and to wash dishes and sometimes wash our cars as well. So most of the cases when we are using tap, basically the water, it comes out in a very fast manner. But if we basically adjust the flow so that it is coming very slowly, then it forms this kind of shape like this. So this kind of flow which is achieved when you open the water tap like this. If I open my water tap, this like a, this kind of flow is a steady flow. So in a steady flow, what we are given usually is, or in case of a tap, we are given that the speed of water uh, at the mouth of the tap. That is how fast the water is coming out of the tap when it is started from the tap. So the speed is given to us as 1.0 meter per second. Very fast, right? But it is given that the flow is steady. So area of cross section of the tap is also given. Area of cross section of the tap is given as capital A. So that capital A is equal to 10 to the power minus 4 meter square. Okay, so this is basically the cross section of the tap. So that means that when the tap is opened, and this is the cross section which the tap encounters first, and at that point, speed is also given to us. So basically, that is the bigger cross section, that is capital A. Then we have a smaller cross section as well, which is somewhere here. So this smaller cross section, small a, that is what we have to find. We'll say that the tap, when the water is descended by some height h. So this h height through which the water has gone down, this height h is equal to 0.15 meters. Okay, so basically, when the water has descended, or we are measuring the water flow 0.5 meters below where the tap opening is. At this point, we have to see that how the flow has narrowed down. This is what you have observed also, right? You would have observed that how the flow narrows down and the flow is steady. So, what would this narrowed cross section be? The reason is very simple to get because of equation of continuity. We know that because of Bernoulli theorem, the speed is going to increase. So when the speed increases, automatically, as per equation of continuity, the cross-section area has to go down because a cross-section area into speed is a constant. Since cross-section area is going down or velocity is going up, the cross-section area must go down. So this is our story. So we'll say A into V is equal to A into V dash. So this implies uh, this is one of the equations which we can use. The other equation is we'll say rho by 2 v square plus whatever height we have at that point. The height is rho g y, rho g h. So be careful how to put height here. Okay, height is basically put off this point. Okay, this is the point where the speed is v. So we'll mark the height of this point. We'll take this point as reference, and this is the height point. So height of this point rho gy, this is coming here, where we have written kinetic energy. That will be equal to the final kinetic energy half rho v dash square. So from this we'll get v dash, which would be pretty easy to get. So we'll get this. This is v square plus 2gh is equal to v dash square. So what was the value which we have taken? The value which we have taken is v is 1. Sorry, this is 1 square plus 2 g is 10, h is 0.15, and v dash is uh, what we have to evaluate. So this implies 1 plus 2 into 10 into 0.15, or 2 into 0.15 is some 0.3. So 0.3 into 10. So that is 3 only. It is equal to v dash square. So this implies v dash is 2 meters per second. So as our velocity is doubling, cross section area will go down. So cross section area will become A into V divided by V dash. So this bigger cross section area A, capital A, is equal to 10 to the power minus 4 into speed v, which is 1 meter per second, divided by v dash, which is 2. So this is half. We can simply write as half only, half into 10 to the power minus 4 meters square. So that means our cross-section area of the fluid 0.15 meter below the opening is half of the original. Let's do next. So we have a tube. So this tube uh, has two cross-section areas. Basically, it is like matlab, getting slimmer at the middle, and then it gets wider at the other end. Okay. So where at the point where it is wide, we'll say this cross-section is some A. At the point where it is very slim, that section we'll say is B. So cross-section A, cross-section A is equal to 1.0 centimeter square, and density of the fluid is given to us as some 1.2 into 10 to the power 3 kg per meter cube. Cross-section B, where the section is slim, is 20 mm square. 20 mm square. Okay, though both of them units will convert them into standard units SI. Then speed of the liquid at A is 10 centimeters per second. Speed of the liquid at A is 10 centimeters per second. And speed of the liquid at B, VB, that is, that we don't know. Okay. Question is, what is the pressure difference between points A and B? That is P A minus PB is what? So first you would have think that okay, how I quickly calculated. How is it possible that I was able to calculate that PA is going to be greater than PB? So the question, the we can answer that by remembering a simple thing. Wherever we have a wider cross section, the streamlines are farther from each other. So we can remember that wherever the streamlines are away from each other, wherever the streamlines are rarer, there the pressure is high. When the streamlines constrict at a point, the pressure is less. By being rarer or being away from each other, what do we mean by that? We say that here the streamlines are rarer, they are away from each other, like their density is relatively less. No more. Oh, sorry, less, yes. And then here the streamlines they constrict. So where the constriction is there we say that there is a pressure fall in pressure. So that means pressure at point B will be lesser and pressure at point A would be more. So from using that, I have written pressure at A minus pressure at B as the pressure difference which we have to find. Okay, because PA is more than PB. Okay, next we'll try to find what is VB. So this is 1 centimeter square into corresponding velocity at A. So this is 10 to the power minus 4. 10 to the power minus 2, and we have squared. So 10 to the power minus 2 squared is 10 to the power minus 4 into uh, 10 centimeters per second. So let us take that in centimeter per second only. V cross section area at B is 20 into 10 to the power minus 6 and corresponding velocity at B in centimeters per second. So this is 10 to the power minus 2. So VB is equal to 10 to the power 3 divided by 20. So that is some 50 centimeters per second. This is the velocity at point P. That is 50 centimeters per second. So now we'll use the Bernoulli theorem. We'll say pressure at A plus half rho, that is whatever value of rho is, into VA square. VA is 10 centimeter per second. That is 10 to the power minus 1. We'll square it. So this will be 10 to the power minus 1. 10 to the power minus 2 is equal to pressure at P plus half rho into velocity of point D, and we'll square it. This is 50 and we have squared it into 10 to the power minus 4. So this is PA minus PB. Its value will be 1.2 10 to the power minus 10 to the power 3 divided by 2 into 2500 divided by 10,000. That is 0.25 minus 0.01. This value is some 1.2 into 0.24 into 10 to the power 3. So this will come out to be some 144 kg per meter per second square. That is pascals. So that is our question. Then we have a wider part. One more question is there, that there is a venturimeter. Um, so it has two cross section, again the one which is wider and the one which is slimmer. So that is actually has a that is the artery of a dog. So basically the wider part of a venturimeter has a cross section equal to that of artery in a dog. So its cross section is given, and we always take the wider part to be capital A. So we have taken capital A here. Its cross section area is given as 8 mm square. Then we are supposed to take the next cross section. The narrower part has an area A equal to 4 mm square, right? Its cross section, it means, is 4 mm square. The pressure drop is 24 pascals. Again, the same thing. Pressure difference is 24 pascals. So, from what I we concluded in the last question, that wherever constriction of streamlines is there, their pressure is less. So pressure would be more at the higher cross section where the area is wide for the artery, and when the area has narrowed down, there will have lower pressure. So this is the pressure difference given to us 24 pascals. The pressure of the drop, the pressure difference is this. What is the speed of blood in the artery? So this is basically the artery cross section. We have to find the speed here, right? And the density of blood is given as 1.06 into 10 ki power 3 kg per meter cube. Okay, so let's begin. So how do you think we'll basically answer this question? I have thought out of a way that we'll be taking that approach. But it's not usually like that. In the questions which we'll take, lot of times when we are doing a question, while doing the question, we develop. Okay, this is the way we'll do the question. So this should be our approach as well. Okay. Because when we are given an exam, we do not have a lot of time to predetermine that how the question will go on, how the answer will come out. Okay. The best way is to take the question head on and then think, and then while jotting down the equations and jotting down all the things, all the basically details, we work out. Okay, this is the point where we are going to get critical, where we have to move forward. So at that point, we have to take a decision that we'll be going forward with this question or not. So that is the thing which we have to actually understand. Most of the cases, when we get to that juncture where we do not know a way forward, we basically waste our time. So that should not be like that. We should keep on moving on. That is the only way that we give value to our time. Okay. And the time given to us by the question paper. And a lot of people, a lot of students have that difficulty. Okay, everyone faces difficulty at that point of the other, and a lot of times we try to overcome the difficulty in different ways. For example, some exceptionally good student, what they would do is they would memorize how to solve that kind of question, this kind of question, and they would just simply try to recall from the memory. Okay, this is the way how we approach this question. This is the way where the question gets critical. This is the question point where we have to assume, okay, this is the dx element, which I already know, which we do not have to think about. Okay, but a lot of times new questions comes, right? Or mm, that is not basically what actually helps the students in getting how to do a question, remembering things, how the question is going to get through is not the way we are going to get a good score in exam. The only way of getting good in a in a question is by getting a lot of practice. By practice, we develop that particular uh, aptitude, or we say a caliber, or what we can say, a different terminology we can come up with. But we develop that uh, persistence of going through with whatever question is throwing at us. So next, we have to basically find what is the speed of the blood in the artery. So half rho v square. Let's say that is the speed of the blood in the artery. So I have written it kinetic energy term, right? Directly writing. So since I, as a lecturer, have given some time in uh, giving some consult to you, So I'm saving my time by directly writing the Bernoulli theorem and writing the equation at those terms. But that won't be optimal for you. You will have to write the equation of continuity first, and from that you will construct everything. And so this is half rho v square plus there is no height. Pressure is there, half rho v uh, dash square plus pressure p dash. This implies now the velocity v dash, where cross-section area is less, the velocity would be more. So this velocity would be two times as much the velocity at R3. This is because the cross-section area has gone half. And in the question which we did the first one, or in the second one, basically the cross-section area halved, right? So as the cross-section area halved, you saw that it was because speed doubled from 1, it went to 2. Here the cross-section area is halving, so you know that the velocity is going to double. So this V becomes 2V. Okay, so this is the one of the way which we can basically master a question if we want to. Okay, it's not necessary that we take these short tricks in doing a question that we directly are writing Bernoulli theorem and we put this 2v here only. Okay, sometimes you can make a mistake, a calculation mistake can occur, lots of things can go wrong. Okay, so that means that we must approach every question on its merit, okay, rather than relating it to what has happened earlier. Okay, so this is half rho v square plus pressure, this half rho 2v square plus pressure. So P minus P dash, this is the pressure difference delta P. So this is given to us 24. This P dash I have marked here. So this would be rho 1.06 10 to the power 3 divided by 2 into 2v square minus v square. So it would be 3v square. So this would be some 8 times 2. 8 times 2 is 16 divided by 1.06 into 10 to the power minus 3 is equal to v square. So upon calculation, what we'll get? So I can write this as 1.6 into 10 to the power minus 4 uh, v square. So this would be some square root of 1.6 we have to do 1 0.60. So this is 1 plus 1 2, 2 times 2 44. So this is some 1.22, 1.22 into 10 to the power minus 2 meters per second would be the speed. Then we have one more question of Venturi meter. So this is a Venturi meter uh, demonstration kind of thing. Okay, because usually you will see Venturi meter when you get to your first year of engineering. Uh, so so मतलब how it looks, that is what we want to see. So it's like a device in which there is a tube attached like this, and there is one more tube like this. So at one of the sections, there is like they have made this kind of, uh, you say, uh, bump in the tube. So because of that bump, there is a constriction. So you would guess, yes, because there is a constriction, so that means the pressure would be less at this point, velocity would be more. So, okay, velocity would be more at this point, that we know. So let's say this point is some A. Here velocity is some B. Here it is VB. It is given that the height of the fluid at this point is more than the height of the fluid somewhere here by a distance of 5 centimeter. So what this means? Basically, this is the rho g y term which contributes the pressure difference. Okay. So the rate at which water flows through the tube is dash. Cross section at A is 6. So cross section at A, we can say cross section area. We can write CA. Cross section area at A is 6, and cross section area at B is 10 mm square. Okay. So it would the equation would be pressure at A plus half rho VA square would be pressure at B plus half rho VB square. Okay. So basically, we are predicting that the velocity at point A would be less, and the velocity at point B or velocity at point A would be more. Since velocity at point A is more, the pressure at point A should be less as per this equation. So that would mean when the pressure is less, and the height of the fluid at that point is basically showing what is the pressure at that point. So uh, this is basically in opposition to what we have reasoned. We are saying that uh, because there is a constriction here, the pressure should be here less, right? The pressure at this point should be less. But as per the figure, the fluid height is more at this point. The pressure is coming out to be more. That means the figure which we have drawn is slightly inaccurate. The pressure, the fluid will have this height 5 centimeter, or the higher fluid would be at this point. It would be somewhere here. So this would be the 5 centimeter point, height point at point B. So we'll write half rho VA square minus VB square is equal to PB minus PA. So we have to find what is the rate of water flow through the fluid. Water is density, which we know. Density of water is some 10 to the power 3 kg. What is the pressure difference that we supposed to know? The pressure difference is simply rho, that is density of water only, g into 5. 5 centimeter means 5 into 10 to the power minus 2. So basically everything rho will cancel out. So this VA square minus VB square is equal to 5 into 10 to the power minus 1, or simply zero point 0.5 into 2. So this is basically into G. So this is 1 only. VA square minus VB square. Next, we want that K, what is the rate of fluid flow? A. Rate of flow of the fluid in the venturimeter, that is Q. That is what is needed in the question. So we will say Q is equal to cross section area A into velocity at A, cross section area B into velocity at B. So this value of Q we can substitute here in VA and VB. So this Q is equal to CA, that is 6 into VA plus 10 into VB. So this uh, we have 0.6 VA is equal to VB into by 10. Q by 10 is equal to this value. 0.6 VA is equal to VB. So in terms of value which we have put this, right? So right, let us put those values here. So this is VA square minus VB square. So VB is zero point 0.6 square is 0.36 VA square. So this is 0.64 VA square. So if we take a square root of that, we'll basically say this is, so we have VA and its square root we'll take this would be 1 upon zero point 0.8. So this is 5 by 4. This is the value of VA. So if you put the value of VA and multiply it with what we are calculating Q. So VA, that is 5 by 4, and multiplied with CA, that is 6, 10 to the power minus 10 to the power minus 6, yes. So this would give us the value of Q in meter per second. So this value will come out to be some 7.5 into 10 to the power minus 6 meter cube per second. So this is the value of Q, rate of flow of fluid at that particular point. Okay, we'll do one last question before basically signing off. So, in the last, or in the last I'm saying in the beginning we discussed an equation called velocity of efflux, right? We poke a hole in a container and water starts coming out. So you'd have seen that kind of water uh, coming out of a tub in your home. Okay, sometimes the plastic bucket which you would have, it might have been broken or cracked because of some use. Okay, because of putting the water again and again and keeping it in the sun, it gets heated and it can get some holes, so water can start coming out or leaking. So in that case, we are very fascinated to know, okay, if there is a leak which is because of an orifice, how fast the water is coming out of that orifice. So there's a question which came on that particular idea, and lots of questions come. So there's a question, basically there's a large open tank and there is a square hole at a depth y, and there is a circular hole at a depth 4y. So at a depth y on the surface of the fluid, we have a square hole and we have a circular hole at a depth of 4y. Okay. So the depth is measured from the level of the fluid. Okay. They are not measured from the top of the tank. We are concerned with the fluid flow. So that means that from the height of the surface of the fluid, we are measuring that depth. So question is to compare what is the quantity flowing out per second from the both holes is same. It is saying same quantity of holes are coming out. Then what is the radius of that circular hole equal to? What is R equal to? If the side of the square hole is given to us as L. It's a pretty easy question, right? You can just say this is root 2Gy, root 2Gy into the square side, L square. Oh, not the square side, square area. The area of the square is L square and that's it. Pretty easy. Velocity of the fluid with which it is coming out into the square area, L square, is equal to the area of the circular hole, that is pi r square, into the velocity with which it is flowing outside, that is root 2 g into y. Y is 4y, right? So that's it. The circular hole was at 4y depth, right? Yes. So then what is R in terms of L? We have to calculate what R is. So this root 2gy is cancelling out that we know. So this is y into L square is equal to 2y, 2 root y into pi r square. So again, this root y and root y cancel. So this is simply uh, L upon square root pi by 2. 2 is also there, is equal to r. So this is a question. This question came in JEE mains. So thanks for joining. Have a good day.